So our first definition, T0 space. Let X tau be a topological space, okay, and U, V be 2 points in X. Then this topological space is said to be a T0 space if for U and V, two distinct points U and V, if there is an open set containing only U and not V, or there is some open set containing only V and not U. What does that mean? For U and V belonging to X, which are distinct, there is some open set U belonging to tau, such that U is contained in U and V is not contained in U. Or there is some V, open set V, such that U is not contained in V and V is contained in V. Okay, V is contained in. Our next definition is T1 space. What does that mean? A topological space X tau is said to be T1 space if both this condition and this condition occur simultaneously. I mean to say that in T0 space, only one of these conditions is satisfied, but in T1 space, both these conditions are satisfied. So there is no OR. In T1 space, all the definitions will be same except this OR. This OR will be written as AND. Okay, that means for 2 distinct points, we can have an open set containing U and an open set containing V and not U. Okay. Now T2 space. What is a T2 space? A topological space X tau is said to be a T2 space if for any 2 point U and V, we can have these two distinct open sets. Okay, this is U and this is V, and this open set is called capital U, this open set is called capital V, and these two open sets are such that U intersection V is phi. That means there is no intersection portion. Okay, so how to write this definition? In topological space X tau, let U and V be two distinct points. So there must exist U and V, two open sets U and V belonging to tau, such that U belongs to U, V belongs to V, and U intersection V is equal to phi. Now take some note. If a space is T2, that means it must be T1, and if a space is T1, it must be T0, but not the other way around. That means if a space is T0, it may not be T1, and if a space is T1, it may not be T2. And to prove this, only a counter example will be sufficient. So as a counter example, that all T0 spaces are not T1 spaces. We take X is equal to A, B, C. Okay, and topology tau is phi X, A and AB. Okay, so if we take this example, then Let us take A and B. These are two distinct points in X, right? Find open set this singleton A that contains A only and not B. Okay. But for B, there is no such open set that contains only B and not A. There is no such open set right here. So, I mean to say that these are two distinct points, A and B. We can find an open set containing A and not B, but there is no such open set that contains B and not A. Any open set that contains B is like this, right? This is AB. So this space x tau is a T1 space, is a T0 space and not a T1 space. It's a T0 space and not a T1 space. If it would be a T1 space, then we can find an open set containing B and not A. Now we will find some counter example to show that all T1 space is not T2 space. Okay, let us take x is equal to R and tau is cofinite topology. Okay, as I mentioned earlier about cofinite topology. So we choose some distinct points uv in X. If possible, let this x tau is a T2 topology. Okay, so there must exist some u and v in tau such that u belongs to capital U and v belongs to capital V. Okay, and u intersection v is phi. Now we know that u and v both belongs to tau. That means x minus u is finite, and so is x minus v. It is also finite, right? So now from this equation we will take u intersection v whole complement is equal to phi complement, which is equal to x. Now by De Morgan's law we will have u complement union v complement is equal to x, and we know that u complement is finite and so is v complement, as I wrote earlier. So this means two finite sets, union of two finite sets is x, but x is equal to R, so this is not possible. So there arises a contradiction. So we can say that this topology x tau is not a T2 topology. Okay, so this is not a T2 topological space, but this is a T1 topological space. Why? Because we can take 2 points u and v, and there exists an open set, call it u, such that u is such that x minus u is equal to v a1 a2 up to an. This contains finite number of elements, so v lies in the complement of u. That means there exists an open set u such that v does not belong to this set u. And similarly, you can also take some open set that contains v and not u. So this is a T1 space as well as T1 space, and since it is T1 space, it is also a T0 space as our note. Okay. Next, definition of normal space. Normal space. A topological space X tau is said to be normal if for any two closed sets, let EF be any two closed sets, then X tau is said to be a normal space if there is some open set U and V belonging to tau such that E is totally contained in U and and F is totally contained in V plus U intersection V is equal to phi. For every pair of closed sets in X, we can have these conditions fulfilled for normal space. Okay. Now, example of any normal space is quite common. You can take X is equal to real number set and tau as standard topology, which is quite common. Okay. So, for any two closed sets, let us take 0, 1. Okay. 0, 1 and 2, 4. These two closed sets, we can always find an open set U and V such that U contains this one and V contains this one and U intersection V is phi. Okay, because there is some -1 to 1.5 and this open set contains this one. So this is U and 1.5 to 5, this is V since this contains this closed interval, right? And U intersection V is of course phi. So here X tau forms a normal space.